Okay, YouTube, in this video we're going to focus on how to evaluate trig functions for any angle. And that is to say that in our last videos that we've been kind of confronting, we've been looking at only angles that exist in right triangles. And so there are always some acute angles that exist that we're finding, say, the sine, cosine, and tangent of. What I'd like to argue is that we could actually take this definition of sine, cosine, and tangent that exists for a right triangle and extend it to exist for any angle in the xy coordinate plane. Now I say note that, well, I don't say, and I put here, and we'll read through it. We say, in the last section we evaluated trig functions of acute angles such as that shown here in 5.32. And so what you're seeing here is this angle in standard position, that is to say that it's leaving from the positive x-axis, and we have this acute angle theta. What we're going to do is we're going to allow this angle theta to be something that is maybe greater than 90. So something that maybe terminates in the second quadrant, as you kind of see here, or maybe wraps around into the third quadrant or into the fourth quadrant. What you're going to see here is this. So long as angle theta is in standard position, we allow some point xy to be on the terminal side of theta. That is to say, we just know some point xy. Then we could also interpret this as being some distance away from the origin here, and also we could drop an altitude back to the x-axis here. But essentially, what you know is if you have a point on the terminal side of your angle, we can always drop an altitude here, and we would know two parts of this triangle. We would know that this distance here is x and this distance is y. This distance r on the outside is going to represent the hypotenuse length. So the hypotenuse, we're going to use the letter r to indicate, and we could always find r if we know x and y just by using the Pythagorean theorem that says that, look, x squared plus y squared is going to be equal to your radius length squared, or your r squared. So now, that being said, essentially we could use the fact that we know some point on the terminal side, x and y, to find the hypotenuse length, and knowing the x and the y leg lengths and the hypotenuse length of r, we could basically find the sine, cosine, and tangent of this right here. And so basically what we're going to do is use our definition of sine, cosine, and tangent to say, as long as I know a point on the terminal side, how could I find their sine, cosine, and tangent? And so let us assume that the angle theta is any angle in standard position. This applies to any angle in standard position. And we let the point P, which is this point xy, be any point on the terminal side of theta. Then we would say that r is equal to the square root of x squared plus y squared, and is the distance from the origin to this point xy as shown above. And so you'll notice that r, we listed here that x squared plus y squared equals r squared. Underneath this we could write that the square root of both sides of this would give us the value of just r, and so we could always say that r is always equal to the square root of x squared plus y squared, and this is always the truth. One thing that we want to make sure that we mention about r is this. We say r is always non-negative. That is to say that we'll always get 0 or a non-negative value there. And so, that being said about r, then we would know some point x. We know a point, and we know the x value, the y value, and the r value. So we would be able to set up a right triangle situation. And if that's the case, then our trig functions here of theta would just be as follows. And so knowing x, y, and r, we could say that the sine of this angle would be opposite over hypotenuse. But in this case, you could see that that would really just be the y value of our point over the r value. And so you see that the sine of our angle theta, if it's in standard position, and if xy is a point on the terminal side, and if r is the distance from that point back to the origin, then we say that the sine value is opposite over hypotenuse, which is really just y over r. Likewise, cosine is going to be over the hypotenuse length, so it's over r, but we say it's x over r. And you can see this up here, we'd say adjacent over hypotenuse would be x over r. And then tangent of our theta here would be y over x, or opposite over adjacent. And so using this definition here, we could basically evaluate the sine, cosine, and tangent, and therefore the cosecant, secant, and cotangent of any angle theta, so long as we know some point on the terminal side and we know this distance r. So the kind of neat thing about this is just we need to know some point on the terminal side, and the distance r we can always find using that point on the terminal side. But we could use this definition to find, say, the sine, cosine, and tangent of any of these angles that you see listed here. And the reason why is because we know some point on the terminal side. So let's go ahead and use this definition of our trig functions here that say we could find the sine, cosine, and tangent of any angle in standard position. So we're going to say let this point P, which is this x and y ordered pair, be a point on the terminal side of some angle theta. It says find each of the 6 trig functions of theta. And so what we're going to do is we are indeed going to find the sine of theta, the cosine of theta, and then the tangent of theta, and then we're going to find their reciprocals next. But essentially what I want you to know is that we would get y over r for our sine, we would get x over r for our cosine, and we get y over x for our tangent. And so all we need to know are these values here. So now knowing that x is -3 and y is -5, we could actually write this down right here. X is -3, y is -5. What we're going to want to do next is we're going to want to find the value of r. And so the neat thing about r is it's always equal to the square root of x squared plus y squared. That is, in this case, we have a -3 as our x and our -5 is the value of y. So when we square these out, what we actually end up with are positive values. We get 9 plus 25 in here, which this comes out to be the square root of 34, which I don't believe reduces. So we're just going to leave this as the square root of 34. And I'm actually going to go write this here. I'm also going to go write this up here. We say, I know x, y, and r. But see, what I want you to see is that we should draw a picture of this. Now, I provided one here. But essentially, we could do this without having to have a sketch whatsoever. Using this sketch, though, what I'd like to do is I would like to drop an altitude back to the x-axis to form our right triangle. And what we're going to do is we're going to fill in everything we know. So we know that this length here is -3. We know that this length is -5. Sorry that this r, I shouldn't have listed it next to this side length here. R is the hypotenuse, and we say r is equal to the root of 34 here. But here's our right triangle where we know the x and the y and the r. So let's go ahead and say for our angle theta here, what we get for y over r would in this case be our y value of our point, which is -5, over the r value, which is the square root of 34. For our cosine value, we would get x over r. Our x value of this point is -3, so we get -3 over the square root of 34. And then for our tangent value, what we're going to get is opposite over adjacent, or y over x in this case, which is -5 over -3. So a few things to say about this. First of all, we do need to rationalize these values here. That is, we're going to get -5 times the square root of 34 over 34. When we take the top and the bottom times the square root of 34. That is to say, when we rationalize these values here that have radicals in the denominator, we get these values instead. And those would be the simplified values, and this would be a positive 5/3. Once we have these, though, we could find their reciprocal functions. So that is to say, cosecant of theta, secant of theta, and cotangent of theta. And what we end up with are the reciprocals of these. Now, one thing I want to mention is it's very, very inconvenient to reciprocate something that you've already rationalized. So when you reciprocate something, I'm always going to recommend you reciprocate the original values you found here. So the reciprocal of -5 over root 34 is root 34 over -5, which I'm just going to put the negative out in front. I'm also going to say that this here, when we reciprocate it, -3 over root 34 would be root 34 over 3, and it would still be negative. And then this last one here, 5/3, this would become 3/5. So these would be the 6 trig function values of the angle theta that you see here. And we were able to obtain these just by knowing x and y and then determining r immediately afterwards. So let's try this again. This time, however, I'm going to give us a point here, or we are given a point, 1, -3, and we want to find the 6 trig functions of theta. So assuming that this is in standard position as we do, I'm going to go ahead and start by drawing the point 1, -3. So that would be 1 to the right and 3 down. And I would say that this point right here, I'm going to label this here, 1, -3, is this point on the terminal side. So I know that because it's in standard position, it has to start on the positive x-axis, and its terminal side has to go through this point. And so assuming that this is some angle, let's assume our angle is between 360 degrees and 0 degrees. That would just mean that it's positive and wrap around this way and come out this way. We'd say, here's our angle theta. But with all of this sketch, what we can do is we can always drop an altitude. We could fill in what we know. So we know that the x value here is 1. We know that the y value is -3. The only value that we don't yet know is r. And we know that that is going to be the square root of x squared plus y squared just because of the Pythagorean theorem. So let's go ahead and put in our 1 and our -3 here. And what we get is the square root of 1 plus 9. Really, we get the square root of 10 is the value of r here. So now we know x. X is 1. We know y. Y is -3. We know r. R is a positive square root of 10. We end up with this guy right here. So going through these then, these are pretty easy to piece together. Let's go ahead and start with our sine, cosine, and tangent of our angle theta. So sine is y over r. That's going to be our y value, -3, over our r value, positive square root of 10. Cosine is also over r, but it's x over r, so we have an x value of 1 over the square root of 10. And then here for tangent, we would get y over x, which is -3 over 1. Before I go ahead and simplify these, I'm going to recommend what I'm actually doing here, which is just go ahead and find the reciprocals before you simplify. So this is going to be 10 over 3, it's negative, root 10 over 3. This one here is going to be root 10 over 1, and this one here is going to be a negative 1/3. And so these ones are pretty established here. And I suppose this we could call this root 10, but we get that guy. This root 10 over 3, negative, so all good. But these two here we're going to rationalize, and so we end up with negative 3 root 10 over 10 for this one. And here we're going to get root 10 over 10 positive. So one thing that I want to kind of mention here before we leave this video is just it's really important to remember that your R value is always considered to be non-negative and is some positive value. So as we go forward, we'll start to see things like sine. Sine will only ever be able to be negative if your y value is negative, or cosine is only ever able to be negative if your x value is negative, and build upon those relationships. Cheers.